Okay, I almost forgot to record, but we just did 16 so far, and this is the work. So you can always pause the video and look at this in more detail if you need to. But we found that 16 should be D. This is 21.4 meters per second. Cool. Okay, 17 then. Oh god, the Doppler effect. Okay. Mariachi's driving in a car at 24 meters per second while playing a note with that frequency. They're chasing them. So I need to like bring up this thing. That was in the document actually that I sent out. I put a link in there. But this, right, like this is a pretty good breakdown, I think, of what sort of happens here. However, there is no case described where the motion is in the same direction, as far as I know, in this document. So we might have to derive that. God help us. Okay. All right, well, let me try this. So, looking at this, it kind of seems like we want to think about the relative velocities of like the observer and the source and the sound wave, right? That's kind of all that these equations are saying. So what I want to say is that we could just take this equation and make this plus down here a minus sign. I think that works. So let me put this equation in. So the observed frequency equals the source frequency times V minus V naught over V minus Vs. So there's this weird thing that happens though, I think, with sound waves where it's like if let's say I'm blowing a note on a trumpet as I walk toward you, like the velocity of that sound wave is the 343 meters per second, right? But also I think that you have to add to that my velocity because it's like almost like I'm throwing the sound, if I'm not mistaken. But let's try this and see what happens. See if my thinking is correct here. So we'll just do the numbers because there's not really much to this aside from numbers. So the source frequency is 880 hertz. And let's do this. We have 300. So the V in this, right? I don't know what convention is used in the textbook or whatever, but the V in this is just 343. The V with no subscript is the speed of sound, right? Is what I'm trying to say. And V, this should be VO. Not that it's a huge deal, but of the observer, right, is 40 meters per second. Now down here we have 343 meters per second, and we have for the source, right, is 24 meters per second. But also, like, just to come back to that discussion about the speed of sound, right, is like if you use these formulas, the ones that I just had up, you don't have to adjust the speed of sound because it should just be already sort of factored into the equations. Like that consideration should be part of the equations already. So let's get the numbers here and see what we get. You know, so strategically speaking, right? Like whenever you work with this stuff, we probably all know this, but like we shouldn't wind up with a negative frequency that doesn't really make any sense. So, you know, probably something to just keep in mind for tomorrow. If you find that you get a negative frequency, you know, something is definitely wonky. So let me make this into a... Okay, so we get 836, yes. That's what we're saying. Okay, so 17, is it D? It's E? Is that right? 918. So it seems like this should be plus, is what it has to be. No, oh, God, I hate this stuff. Okay. Let me just try this. Let me look at this one more time. Yeah, they are. That's true. So both have to be plus. Okay. So it looks like you could write this. You could write these equations, like you could just write one equation that covers all these cases, if I'm not mistaken. But you have to use the idea of relative velocities. So let me try to do that. I don't want to spend too much time on this one, but it would be nice to get the correct answer. So if we look at, like, for instance, this form, though it doesn't really matter, it's like here what we have is in the numerator. I'll zoom in a little bit. In the numerator, it's like we have the speed of sound with respect to the observer, and here like the speed of sound with respect to the source. So let me try it like this. Speed of sound with respect to, and I have to use like a fancy O here to keep it separate because I don't want to mix up the S's, and I'm gonna do the same thing for S. So V of sound with respect to source. So the script O indicates observer, right? The script S indicates source, and the V sub S, like this S here, just indicates sound, right? So we're just talking about the relative velocities. And this, if I'm not mistaken, like could work in any possible case, right? Because you don't have to have like 4 different equations. But you do have to kind of be comfortable with the idea of relative velocity, right, for this to work out. So let me see if this works in this particular case. Okay, so the frequency of the source. And then what we do is we say, no, but I think this way we're gonna get the same thing. They're following. You know what? Let me come back to this one. I hate this. We'll save this one for the end. Maybe something will come to me, but it looks like people have the answer in chat, right? It's just plus over plus, right? Is what people are saying, and it looks like that works. Yeah. So We can come back to this though if people want to hear me or watch me struggle more with 174 material. Okay. A sprinter runs at constant speed of 8.1 meters per second. The drag force on the runner is 29.5 newtons. What is the rate at which the runner is doing work to maintain her constant speed? Yeah, this one isn't so bad because we talked about. I'll do this again because it's really not difficult. But remember that work is defined, right, to be in one dimension. Let's say, right, if we're just talking about motion happening in the horizontal direction, we could write it like this, essentially. It's just a force times a displacement, right? So F delta X. Now, power, right, is defined to be the time rate at which work is done. So we could say something like this. It's just defined to be the work over a time interval. Now, if we write that the work is F delta X on top, and then delta T is still just in the numerator, right? Because nothing's changed about that. Then what we find is that F is, or F times delta X over delta T is the power, right? i.e. the rate at which the work is being done. And so this is just F V bar, right? Not hat. V bar. Where's the bar? There we go. So let's check this because the force is 29.5 and the average or constant speed is 8.1. And we get that it's 239 watts, right? So 18 should be A, and it is. So this is good. Let me just put the number in here. 239 watts, awesome. Okay, 19. Small pine tree is a mass of 19 kilograms. Its center of mass is located 0.87 meters from the ground. Its trunk is sawed through at ground level, causing the tree to fall, with the severed trunk acting as the pivot point. At the instant the falling tree makes a 16-degree angle with the vertical, the angular acceleration of the tree is 2.6 radians per second. That should be seconds squared, right? But who am I to judge? What is the moment of inertia of the tree? So let's make a diagram here. Unfortunately, we got to do that. And so the tree is at a 16-degree angle with the vertical, right? So we could draw it like this maybe. This is the vertical. Let me make this thicker. This is my angle. Now the force, let's see. The force is going to act at 0.87 meters from the axis of rotation to the point of application of the force, right? So if the force, the gravitational force is acting, say, here, straight down, then my D, which is the 0.87 meters, is going to look like this, right? So we just need to make sure that we get the right component of the gravitational force here for the torque. And what we want, right, is we want the component that is perpendicular to the line drawn from the axis of rotation, right, which could be here maybe, to the point where the force is being applied. So what that means is we want to consider this component of the gravitational force when we calculate our torque, right? And so we could just call this mg perpendicular, and we're good to go. So we also have to be careful with the trig, right? Because this angle is going to be not the 16 degrees, but it's going to be 74 degrees, right? So I'll call it phi instead of theta. Phi, like so. And I think we're good now because it doesn't seem like there are any other torques acting on this thing, right? So we can just write this out. We would write the net torque, and we'll take the z-axis to be the axis passing through the point of rotation there, right? Is going to be, now if we want to be like technically correct here, we put a negative sign, right? Because we can see that this component of the gravitational force is going to tend to make the tree rotate clockwise, right? Now, this should be mg cosine phi, right, equals negative I alpha. So we just divide both sides by alpha, and we find that I should be mg cosine phi divided by alpha. Or equivalently, right, because phi and theta are complementary, it could also be mg sine theta over alpha, right? However you prefer to think about it, I guess. So we'll get a number for this. We want 19 times 9.81, and I'll just do cosine of 76 degrees divided by, wow, yes I do, that amazing catch. It should be mgd, my bad. And so the way that you could see this is by thinking about the dimensions, right? So don't be like me and think about dimensions, because we would see that what I wrote was a force. No, wait, it wasn't a force. I don't even know that what I wrote has a sensible interpretation, okay, as far as the dimensions go. So don't forget about that. That's good. And then we divide by 2.6. So thanks to Abby for catching that. We get 15. That's not a choice, though. What's going on here? 0.87. Oh, I did the wrong angle. Jeez, I'm a mess, guys. It should be 74. I don't know how much of a difference that's going to make, but... wow, a lot of a difference, okay. So it works out to be C, right? Because this is about 17.2 kilogram meters squared. So let's make sure that 19 is supposed to be C. Yes, a 19C. Okay, 19 is C. Now, what could be, like, what I think is tricky for people with problems like this, aside from forgetting the radius, is that you need to make sure that you get the trig correct, right? And so tomorrow, like, if and when you have a problem involving torque, just make sure that you draw like a very nice diagram and, you know, label everything as accurately as you can, and that will really help, right? Also, not forgetting the radius. Okay, that's probably good. Let's see here. Two skydivers with identical masses and drag coefficients, but different cross-sectional areas are falling at their terminal velocities. Which statement below is true? This is, like, I think something that looks a bit more complicated than it actually is, because remember that at terminal velocity, we just have that the magnitude of the drag force equals the magnitude of the gravitational force, right? Terminal velocity means the velocity is not changing, right? It's like the final velocity. There's no more acceleration to be experienced by the object. And so let's see what choice here could be correct. Well, because their masses are the same, it looks like A and B are not going to be the correct choices, right? I want to say that it should be D. The drag force on them should be the same, right? Like we were just talking about, because they're at terminal velocity. So let's see if that's correct. We're saying 20 is D, right? And it is D. Okay, cool. So that was that. All right. Why is C wrong? The drag force does work on both skydivers at the same rate. What my gut says is that their terminal velocities are not the same. Yeah, no. So I mean, this is so. What is the drag force? We can talk about this. The drag force is defined to be 1/2 rho C, right? Some constant that just sort of empirically or experimentally determined A v squared, right? Somebody tell me if this is. Well, I'll look it up real quick. So we use quadratic drag, which is, yeah, this. Okay, 1/2 rho v squared C times the cross section. A is the cross sectional area, right? So this is the equation that we're using. So the thing is, we could solve this for the velocity and see that just because the drag force on them is the same doesn't mean their velocities are the same, right? So they have different, so the point is, I think that they have different terminal velocities. And that eliminates C, right? Because the rate at which the work is done depends on their terminal velocity, the value of it. So we can't say that the work being done on both by the drag force is the same. And we can't say that the terminal velocity of both is the same because they have different drag coefficients and they have different areas, right? We don't know that. Basically, they would have to have the same product of their C and A values for some of these other choices to work, and we don't know that that's the case. Because there's any number of combinations of numbers that we could plug into the right-hand side of this equation to get that the drag force is the same for two different objects or people, right? And so that's why. Is this clear? Is it making sense? Are people finding this explanation satisfactory? Okay, cool. All right, good. Okay, 21. So starting at rest on the top of a 23-meter hill, a child on a sled rides down the hill onto a flat plane and slows to a stop due to a combination of friction and air resistance. The child traveled a distance of 39.1 meters. What was the magnitude of the average force from friction and air resistance on the sled? The combined mass of the child and sled is 32 kilograms. Okay, so this is a combination of work and energy, right? So we use conservation of energy to get the speed of the child in the sled at the bottom of the hill, which isn't so bad. We could just write something like mgh equals 1/2 m v squared, right? Now, work energy theorem says something like the work done on an object equals its change in kinetic energy. And it's not like 100% clear here that the child comes to a stop, but that's sort of like the only reasonable way to interpret this, right? So we could say that in this case, let me fill in the right-hand side of this equation first. The final kinetic energy is 0 because the kid comes to a stop, right? And the initial kinetic energy is what we found here. It's 1/2 mv squared, right? Or we could just write from conservation of energy that the 1/2 mv squared is just mgh. So let's just do that because we know h. We don't have to do any intermediate steps. And then the work done is just going to be the average force times the distance. So we could write this. We could write negative F bar. Not that it matters too terribly much, but it's good to just be precise, right? And we find that F bar D equals mgh. So this. And we just divide both sides by D and we get the force, right? So let's do that. Mass was 32, G is 9.81, H is 23, and D is 39.1, right? So 185 newtons, right? So we think it probably is going to be B. Let's see what we got here. 21. B. Cool. So this is good. Let me know if anything here didn't make sense, but I think that probably all comfortable with it, but if not, you know, just tell me. Okay. A simple pendulum is pulled to the left and then released. The release point is shaded gray in the figure. The first time the mass passes through point 1, swinging toward the right, what is the approximate direction of its net acceleration? I think here it's probably a good idea to draw the free body diagram. Or rather just think about the accelerations. Now, we know that its tangential speed must be increasing, right? Because at the top, it has no tangential speed, and at the bottom, right, it has the maximum tangential speed. So what I would be inclined to do is make a crappy sketch of it at 1. So this is the bob or whatever it's called, right? And we would have that the centripetal acceleration must point towards the center of the circle through which this thing is moving. And this is circular, right? Because it's always a constant distance from the point of suspension. And the tangential acceleration must point like this for the reasons we just discussed. And so if we were just to like sort of think of what the vector sum of these two looks like, right? Because the total acceleration is just the vector sum of these two, it's going to be like that approximately, right? And so it looks like E should be the correct choice here. And let's confirm that it is. Wait, C. It's saying C? Okay, I think that's just because my drawing is crappy. Let me do this. This is what I should have done originally. I don't know that that's good. The acceleration due to gravity. That is, I think, factored into the tangential, is it not? We could also just solve for it, I guess, if people would feel better about that, though. Maybe that's the move. But we need the free body diagram anyway. I don't like this question. Thankfully, it's been removed. But okay, we could just do the stuff. So if we do the free body diagram, what we're talking about 0.1, yep. What we would have is we would have tension pointing like this, and the gravitational force pointing like that, right? And that's it. So let's just try it like this. So we also would need to know what angle this makes with like the vertical here. So that would be this, right? This angle. I don't know. It looks like it's like 30 degrees maybe. Because that angle, right, is the same as that angle is the same as the angle that the gravitational force makes with respect to this radial or centripetal line, right? It's the same as this angle. So what we could do is we could say T minus mg cosine theta. I don't know if this is really going to get us anywhere, though. mv squared over r. I don't know that I want to do it this way, just because I guess there's too many unknowns. Let me just hopefully convince you that the correct answer is C, I guess, because let me redraw it. And I'll just say there's nothing like this on the exam tomorrow. And I think that probably this was removed because they didn't think it was a good question because it's a little ambiguous, right? Depending on, I mean, because it's just kind of visually looking at this thing and sort of, you know, saying where this vector is supposed to point, which is not very precise. So this is, it's really not visible. This is my centripetal acceleration. Okay, this is my tangential acceleration. We don't know how these compare, right? Like how their magnitudes compare, but it's not unreasonable to say that adding these two together gives you something that looks like this, right? Technically, it should be longer because, you know, it would be the sum of the components of each of those that points to the right. But like, I think that C is okay. I think C kind of makes sense. It's just that I didn't do a great job with my sketch here. And it's hard because it's MS Paint, right? And we're saying C is the correct answer. And it is. Okay. Are people okay with that? Let's see here. When rolled down the same ramp, starting from rest at the top, a solid sphere will always make it to the bottom faster than a hollow sphere, even if they have different masses and/or radii. Why? So this would be a good one to approach just by elimination, because there, I think, are definitely some things here that we can just get rid of like offhand because we know they're wrong. And so we could say that A is incorrect because they both start at the top of the ramp, so they both have the same initial potential energy, right? So we can get rid of A. We can't say that the solid sphere always has a smaller moment of inertia than the hollow sphere because you know, we don't know anything about their masses or radii, right? So we can eliminate B, I believe, also. For similar reasons, we can eliminate C because we don't know anything definite about their masses or radii. D looks good, potentially, right? Because solid sphere always uses a smaller fraction of its mechanical energy to rotate. And I think that we could convince ourselves of this by looking at the formulas for their moments of inertia. Let's do this. Let me make this qualitative, right? So let's say that the kinetic energy of an object that's rolling, right, without slipping, can always be expressed as the sum of the translational kinetic energy and the rotational kinetic energy, right? So translational kinetic energy is pretty straightforward. It's just 1/2 mv squared, right? We've been working with that for a bit now. The rotational kinetic energy is 1/2 I omega squared, right? Now, what we want to do is we want to use the no slip condition. We want to use the no slip condition to basically eliminate omega in favor of V, right? So we would use, remember, right, that V is our omega. This is our no slip condition. And so we'll just keep I as is for the time being. Now, omega squared is just V over R quantity squared, right? And then the last thing to do is to note that the moment of inertia in general for pretty much all the objects that we are familiar with, right? Like whether it's a disk or a hollow sphere or a solid sphere, pretty much anything circular or even non-circular, really, can be written like this. It can just be written as some numerical coefficient times the mass times the radius or length squared, right? If we're talking about a rod, it would be like the length. And so we could rewrite this as alpha mr squared times v squared over r squared. And we see that there's no dependence on the radius here, right? It ends up canceling out. I'll just write v squared here. So what this tells us, right, is that 1/2 mv squared plus alpha times 1/2 mv squared is the total kinetic energy of an object. And alpha, remember, is just a number, right? So let me bring up a table of moments of inertia. Because I think, let's see here. So we want to compare a hollow sphere and a solid sphere, right? So for hollow sphere, total kinetic energy is going to be 1/2 mv squared plus, what is alpha for the hollow sphere? It's 2/3, right? 2/3, 1/2 mv squared. And for the solid sphere, K total is going to be 1/2 mv squared. By a similar line of reasoning, right, 2/5 times 1/2 mv squared. And so with this, is this clear, like what I'm doing here? I'm just like doing the algebra to convince us that there's no dependence on basically the radius. And we could even see actually there's no dependence on the mass if we look at conservation of energy, right? Because what we would actually be doing here is saying mgh equals the kinetic energy at the bottom. And so we could even say that the in this situation there's no dependence on the mass when we consider like the whole sort of sum of events, I guess. And so let's see here. So this, it looks like the solid sphere uses a smaller fraction of its mechanical energy to rotate, right? Because we could just, one more time rewriting this, we could write that this is k translational plus 2/5 k translational, where this part is the rotational bit. Why did I get rid of alpha? Well, I didn't get rid of it. I just plugged in what it is for the hollow sphere and the solid sphere, right? Because remember looking at this table of moments of inertia, we saw that for, maybe you can't see this, it's probably kind of small, but like for a solid sphere, this alpha is just 2/5, and for a hollow sphere, alpha is 2/3, right? So there's that, and then we could rewrite this just because, why not, plus 2/3 kt, and 2/5 is less than 2/3, right? And so we could say that the solid sphere always uses a smaller fraction of its mechanical energy to rotate. And so 23 should be D. Let's see what we get here. And it is D. Okay, so that was a bit convoluted, but hopefully like we are a little bit clearer on like the dependence of, or the lack of dependence rather, on the radius of the object that's rolling, right? As long as we're assuming rolling without slipping, which we pretty much always will. Okay, cool. Is this good for everybody? Does it make sense? Let me know if there's any confusion. Okay, 24. Actually, we're almost there. Rubber cord is Young's modulus of that. Cross-sectional area, length of whatever. Okay, a mass of 0.54 kilograms is hung from the cord and set oscillating. What is the period of oscillation? Okay. So conceptually, a big thing to note here is that the fact that this is vertical does not change the angular frequency of the oscillations, right? I think Hatred said that he's talked about this a bunch in class, and if some of you are like neuro students by chance, I think he's pretty good about mentioning this too, but like it doesn't matter that this is vertical. So are we all good with that idea? You could show this with the math and stuff, but I don't want to do that unless somebody thinks it would be helpful. So let's just remember what Young's modulus is, right? What it's defined to be. It's like stress over strain, or, you know, more usefully, it's just the force over the cross-sectional area divided by the fractional change in length of the object, right? And so we need to get a spring constant out of this, and the way that we do this is we just sort of analogize with Hooke's law. So I'm going to rewrite this a few times just to make it hopefully clear. Right, and so what we could do is, if we just keep going like this, we could write something like F delta L times L naught over A is Young's modulus, right? We haven't done anything other than just sort of re-express what Young's modulus is. But the reason that I'm doing this is because we want to remember, and I think I said this during the equation sheet session, we want to remember that Hooke's law tells us that F, the spring force, is given by some constant times the displacement, right? So we just can think about magnitudes here and write this. And keep going and find that K, right, is defined to be the force the object experiences divided by its displacement from the equilibrium position. Now, for an object like a semi-rigid object, its equilibrium position is just going to be, well, it's going to be related to its equilibrium length, right? And so what we get is this, is we get the Young's modulus, and I'll use a different K here just to indicate that it's not the usual spring constant that we think about, is given by the equilibrium length, or rather Young's modulus equals the effective spring constant times the equilibrium length over the cross-sectional area, right, is what we are saying. Now, this is not something you would have to derive on the fly, right? Like this is just something I'm doing, but like you could put this on your equation sheet, of course, right? So hopefully it wouldn't take you as long as it's taking me right now. And so then what we do, right, we just solve for K. We see that it should be YA over L naught. Yeah, YA over L naught. Yeah, I don't use E because I don't know why anybody would ever do that when E is already so overburdened, right? We never use Y for anything, but yeah, that's fine. So we have our spring constant. It's this. Then our angular frequency, right, is just the square root of the spring constant over the mass, right? And then we also need to remember that the period is given by 2 pi over the angular frequency, right? So we find that this should be 2 pi divided by the square root of K over M, just like we would for a regular oscillator. And let's figure out what this is numerically. So K is going to be 3.2 times 10 to the 6th. Oh, we have to convert. This is a real pain in the ass. We have to convert from centimeters to meters, right? And I would bet that one of these choices is what you would get if you didn't convert, right? If you just forgot. So is everybody okay with converting from centimeters to meters? We just have to remember to square the conversion factor. That's the big thing, right? And so I shouldn't have said from centimeters to meters. I should have said from centimeters squared to meters squared, because that's what really could mess you up here. Well, we just want to remember that 100 centimeters, sorry, 1 meter is 100 centimeters, right? And then we square the conversion factor. That's the big thing. So what were we doing? We were doing K. And L naught is 0.63. Okay, so this is our K. It's rather large. We want to do square root of K divided by the mass, 0.454. So this is our omega, right? It's about 54 radians per second. And then we do 2 pi divided by that. And we're getting something that's not a choice. Huh, what's going on here? Oh, I have a factor of, wow, okay, I have a factor of 10 off in my answer. I don't know if it's going to fix it, though. Oh, it does. Or does it? Yeah, it does. Amazing. Okay, so I was off. I just wrote a 7 in the exponent when I should have written a 6, right? So everything that I did was good. I just put the wrong number in, and that's why we hate numbers, right? Numbers suck. So it should be A, and we see that it is. Okay, was that clear? I know it was a bit convoluted, but really the challenge, I think, of this problem was just using Young's modulus to get a spring constant. That was really the sort of meat and potatoes of it, right? And so that's not something like I mentioned, right, that you'll have to derive on the fly, because you could just write this equation down on your sheet, right? This is apparently it works. Okay, cool. All right, 25, and then we can move on to, well, yeah, maybe we should go back to that stupid Doppler shift problem. What is the value of okay. Yeah, this is annoying. So you could just brute force this, right? You could just do the cross product using the equation for it. Do people have that like on their sheets? I don't know that I mean, I could derive it. I don't know. I don't remember it off the top of my. I'll bring it up. Let me see. Cross product formula. Because we don't want just like the magnitude is given by the magnitudes multiplied together times the sine of the angle between them. Like what would be useful here is the component form. Let me see if I can find this. I don't know that I even... Because I could just have Mathematica do it. Let's do that. Better than me trying to scour the internet for it. Even though I feel like it should be easy to find. So this is what I meant, right? Is that the cross product, right, of, let's say, two vectors u and v. Is everybody okay if I write this as a column vector? I don't want to do like, I don't want to do unit vectors or anything like that if I can avoid it. But we find that the x component is just uy vz minus uz vy. We find that the y component is uz vx minus ux vz, and we find that the z component is ux vy minus uy vx. So this is the equation that I was talking about, right? Because we also have the other one that just says that it's uv sine of the angle between them, and then we can put an n hat here to indicate that this vector is perpendicular to both u and v, right? And here, so here this is actually not so terrible because we can use our intuition about the cross product to convince ourselves that the results of taking like this cross product here, this inner one, this inner expression, is not going to have an x or y component because these two vectors are both oriented in the xy plane, right? So they're only going to have a z component, so we don't have to worry about this term or this term, sorry, the top term, right? This x component here. We just have to focus on this. And so if we say, right, that u cross v is simply, this is what I'm saying, it's this, which gives us the z component times, oh wait, no, I'm tripping. I hate the IJK notation, I never use it, so what I said was not correct. But I mean, what I said was true. It's just not true for this particular problem, because I thought that they were both in the xy plane, but this is actually not. This has a z component, right? So what I would do is I would just have my calculator do it, right? Can everybody do cross products on their calculators? But like I can tell you, I don't know if this is super helpful, but I can also just have the computer do it, right? So I mean, all you need is like this formula really when it comes down to it. You just need this. All right, okay, all right, fuck it. Let's just do it. Okay, so then we have to just plug in what all these things are. So what I want to do is I want to just be careful here. I want to write something like, I want to write that u, and I want to put this in probably the form of an ordered triple here. So u is going to be 4, 1, 0, right? These are just the components of u. And v is going to be 0, 3, -7, right? So this tells us that u sub x is 4, u sub y is 1, u sub z is 0, and v sub x is 0, v sub y is 3, and v sub z is -7. But interestingly enough, right, remember that when we take the dot product, if we take the dot product here with the unit vector y hat, then we only care about the y component of this. So we could just calculate that, because it doesn't matter what is in the x or z component, because we're going to get rid of that anyway when we take the dot product, right? Okay, so if you want to get it on your calculator, like maybe you could just find a YouTube video where they tell you how to program it in or something like that. I feel like if you have like a nice TI though, it should already be in there. I know my like crappy little $20 calculator from Texas Instruments does it, so I'd be shocked if like a TI 83 or better doesn't do it. But it's either going to be already in there, or you could just look up how to program it in, right? But I'm going to keep going with this because we're almost there. Okay, so but like I was saying, we only need to focus on the y component here, because we are going to end up dotting this whole thing with y hat anyway, right? Which means that whatever is attached to x hat and attached to z hat doesn't matter. And so we could just put like literally just dot 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 here, right? And dot 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 here. Doesn't matter. So we just have to actually calculate this, and we'll do this carefully. We want to focus on this part. And so u sub z times v sub x is just 0 times 0. And then we subtract u sub x times v sub z, which is 4 times -7, right? And this should equal 28 for the y component. 28. Then let's talk about the dot product too, just because it's, you know, a thing here. let's use a different notation. We'll say that like A dot B is just given by the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. Yeah, no, that's why IJK is stupid. But I think I is x, j is y, and k is z. Is it just goes in alphabetical order. But yeah, it's dumb. I just write x, y, z. Anyway, when we end up dotting this though with j, right? Remember j hat? I'm so salty about this. Like, you're a physicist. Why would you use IJK notation? But remember that j hat is just this. It's just 0, 1, 0. Because it's the unit vector, right? Which means it has length 1 that points in the y direction. And that is what this vector does. So when we take the dot product of this and this, it just works out to be 28. Because this is what the dot product is, right? I want you to all promise me you're never going to use IJK notation. I think they do it in math, and it makes a little sense there because math is supposed to be like more general, but I don't understand why we would ever do this in physics. Is this okay? Are people feeling all right about this? I guess like what I could do is if it was dot. Well, this is just a definition, right? J hat is just the unit vector, and like I could say like equivalent or not equivalently, but similarly that I hat is 1, 0, 0, right? Yeah, you could, okay. I mean, you could get it on your calculator. If somebody finds like a link, feel free to put that in chat. That might be helpful. This is k hat, right? Like so. I don't think, like, I honestly don't think this is going to be important for the exam tomorrow anyway, but like you will have to learn about this stuff at some point in more detail, probably in a math class. So like don't stress about this too much, I guess. As far as the exam is concerned tomorrow. Yeah. I don't know. Hopefully we learned a little bit about math though. So this is what you do. I'm going to stop talking about this damn problem now because, like I said, it's not going to be important. Let's come back to this stupid Doppler shift problem. I think we did pretty good with everything else, right? This is just the only one that I wasn't able to get. Let's see. Banditos are chasing a mariachi. I want to try it. Let me bring up that thing again. So this is what we were looking at, right? And we have, let's make this definite. Let's say everybody's moving to the right. So the car is driving to the right where the 880 hertz frequency signal is being emitted. And the banditos are in a car driving to the right as well. Or maybe to the left. because it feels like we should just be able to take... Okay. Nothing actually 918 hertz. Okay. Let me just think about this for a second. But people were saying plus plus gets you there, right? Can somebody confirm that? Plus plus gets it. Okay. Mm. What if we just say that when the source and observer are moving in the same direction, you just use plus plus? Because we already have like all the other cases covered here, so that's just like one more to put maybe on your sheet of notes. Is just like when, so we have like, for instance, when they're moving away from each other, when they're moving toward each other. Now, when they're moving in the same direction, you just use plus plus. And so that covers, I guess, all the cases, right? And then we should be fine. Are we good with that? Do we like that? I want to do it just to make sure it works, because I would feel bad if I was lying to everybody. But so what we're saying, and somebody in chat can confirm this or deny it, I guess, but we could say V plus V naught, or VO, right, over V plus VS is what gives us the correct answer here, because they're moving in the same direction. Yeah. So what Ethan's saying, that PowerPoint is not on Canvas. I can give you the link in chat though if you want. I put it in like the equation sheet that I sent out, but if you're not one of my students, you wouldn't have gotten that. So let me just do this. There's that, and then we will just confirm this, and then we can move on. Oops. So we want to do... Uh, 343 plus 40 over 343 plus 24, right? Times 880. Okay, there we go. Yeah, so same direction is plus plus. All right. How do you choose plus plus over minus minus? Let me look at that thing again. So it depends on how the source is moving with respect to the sound wave, right? Is how you choose that basically. Because for instance, well, it depends on both, right? It depends on how the observer and the source are moving with respect to the sound wave. But let's focus on the observer. And so in this case, right, where we see that there's there's plus on top, the observer and sound wave are moving in opposite directions. And this makes sense because this is the relative velocity basically between them, right? This is the rate at which the distance between them is closing. Now, here where the observer and the sound wave are moving in the same direction, it's still the relative velocity, because it's almost like we can think about the observer being at 0 and the sound wave moving faster, right? And the last thing to think about, though, is just that, remember, you should always get a positive frequency when you do this. And so if you're thinking about this in terms of the relative speeds or velocities of the sound wave and the observer, or the sound wave and the source, and you get a negative number for your frequency, then you know that you just probably did it in the wrong order, right? You subtracted in the wrong order. Because you should never get a negative frequency, okay? But I think that this sort of has it, like, if you just convince yourself that these are all these terms, right? This V minus V, VO, this V plus VS, this V plus VO, this V minus VS, these are all relative velocities, right? And if you can just internalize that, you're good, and you can do this for every possible case. So yeah, hopefully that helps at least a little bit. Let's see here. I'm gonna start looking at. Are we good with this, with the practice exam that was given out, the official one? Because we can move on to this. We could do like 1 or 2 of these before I have to go, and then if there's, like I said, if there's interest, when I get back in, we can keep going for a little bit longer. Where's my? Here we go. Is there anyone? Let's see. Is there anyone from the practice final that I gave out that anybody wants to look at? So somebody's asking about 14 and 3. Okay, let's look at 14 then. See if there's a trick to it. Maybe, depends on how you think about it, I guess. But let's start with this one since it was asked about first. Okay, so let's say the only forces acting on the book are the gravitational force exerted by the Earth, obviously, right? And the normal force exerted by the table. No, there's no answer key. It's in my brain. You don't want to go in there. So the only forces acting on the book are the gravitational force exerted by the Earth and the normal force exerted by the table. So there's actually like there's 2 sets of correct answers here, because you could say that the force that the book exerts on the table is part of the action-reaction pair that the table, or involving the force, right? Wow. Involving the normal force that the table exerts on the book, right? So that would be one action-reaction pair. The point of this question is to make sure that you understand that the gravitational force and the normal force are not an action-reaction pair, right? Because, and at the most basic level, it's because these are both forces being exerted on the book, right? And remember, an action-reaction pair is like where one object exerts a force on another object, and the other object exerts a force on the first object. So there's actually a few different correct answers here, but like, as long as you don't think that it's the normal force and the gravitational force, then you're fine, right? Are we all good with that idea that it's not the normal force and the gravitational force? Because that was really the point of this. So for who asked about that, right? Are you willing to say if you're good with that? Because then we could look at 3. All right, somebody's saying yes. Okay, cool. Let's look at 3 then. This is a pretty typical thing to be asked about, right? Like as far as for this kind of class, and there's a few different. This is an involved one, right? It's like some of these I think are relatively simple, but this one is a little more in depth. And I'll just outline for you what you would do here. You would want to apply conservation of momentum. Linear momentum, right? I feel like I should probably say that, to the collision between the bullet and the block, right? Because we can't do conservation of energy here because this is an inelastic collision, right? This is the paradigm of inelastic collisions where, you know, the two objects stick together and move as one after the collision, right? So we have to do conservation of momentum here. And we would just do this. We would just say the initial momentum in the x direction equals the final momentum in the x direction. Now, the initial momentum here is given by little mv, right? This is the momentum of the bullet. And if the bob is at rest initially, then it has no contribution to the momentum. Then after they move together, right, we could say that the final momentum is just their masses added together, and I'm going to write big V here for their shared velocity. And so we find that big V is going to be little m little v divided by the sum of the masses, right? At this point, we can now use conservation of energy because there are no non-conservative forces that are doing work, right? As the block and the bullet together start to swing up. So what we could do is we could just say that the center of mass of the block is our y=0 position, right? So essentially all the kinetic energy is converted to gravitational potential energy. So we could write something like this. We could write conservation of energy, and the only form of energy after the collision, right after the bullet is fully embedded in the block, is kinetic. So it's this, where big V is, of course, of this, right? So this is, it can be a little bit of algebra, but I'll just talk about what you would do here. And then we just set this equal to the gravitational potential energy finally, right? Because the block and the bullet together experience a change in their y position, right? So it could be this. Now, the mass actually cancels out here, which is nice. So we have simply that v squared equals, or v squared over 2 equals gh. And finally, that h equals big V squared over 2g, right? Now this is like the crux of the problem. Basically, whatever you have to do after this is just like trig. And the way that you do this, I'm gonna have to make a sketch here and hopefully it's not awful. I think I can actually use this. That's convenient. So let me get rid of some of this crap here. And what we're kind of thinking about, right, is just imagine that this little bob is like the block, or it's not even a block, it's a bob, right? Before the bullet hits it. It's just hanging there, right? It's chilling. And then this is the maximum height that the bullet and I'm gonna say blob. The bullet and bob together attain, right? So we say that this is y=0, right? That's what we said is like the equilibrium position of the bob was our y equals 0 position, and then it comes to this height, h, right? And so what we want to do is we want to solve for this angle, this theta here. Or no, we don't want to solve for that. But we don't need to. We don't need to solve for it, but we need to think about it. Okay. Now the trick here is to note that the length of the cord or the rod, what I don't even remember what I wrote at this point, is L. Yeah, you're right. I misspoke. We're not solving for theta. We have theta, right? And the trick here is to make this into a right triangle, like this, and then use some trig. So what we have here is that if this height is h and the total length of the rod is L, then the length of this bit is L minus h. Right? And so what we do is we just write cosine of that, right? Cosine theta is adjacent over hypotenuse, right? So it's L minus h over L, from which we see that L minus h equals L cosine theta, otherwise known as h equals L times 1 minus cosine theta, right? So then what we do is you're right, like I wasn't careful here because we want to, no, I'm good. I'm good. Because we have h now in terms of the length of the rod and the angle, right? And so from this equation, we see that L times 1 minus cosine theta equals v squared over 2g, and then getting big V allows us to get the little v, right? And so this is a long problem, okay? So I don't think that you would have to do anything that takes this long on the exam tomorrow, but it does cover like a few different concepts that are important, right? So this is a good one to make sure you understand. Now, I think, like I said, I think the tricky thing here is this part, right? This is what seems to mess people up, is the geometry or the trig, right? But everything else is, I think, mostly straightforward. Is this good for Abby, who asked about number 3? Do you see what you're supposed to do here now? I don't know if these numbers are realistic, honestly, but like the process is good. This is a good approach here. I mean, it's as far as I know, the only correct way to do it. Okay, I do have to end here. I will return though. Like, let's say, I don't know exactly when, but I thought since it is an inelastic collision, energy isn't conserved. Well, it's conserved after the inelastic collision takes place, right? Because after the bullet strikes the block, and once it's fully embedded, then you can apply conservation of energy. Because after that point, there's no change, say, to like the way the masses are configured in the system. So it's like for the first part you do conservation of momentum, and the second part then you do conservation of energy. So it's okay. Yeah. Okay, but I do need to go. I'll just plan on being back around 10. We'll see how many people are here. And we can keep going with this, or I can just take questions about other stuff. Probably not the Doppler effect, but anything else would be fair game. And yeah, I'll see you guys later.